Before starting this presentation on the experiments made and the demonstration of the principles under investigation, we would first like to define the main terms that we are going to use.
First, what is stress exactly? The concept of stress is a measure of the average amount of force exerted per unit area of a surface within a deformable body on which internal forces act. In other words, stress is the internal resistance of a material to the distorting effects of an external force. This resistance tends to make the atoms of the material in question come back to their original position. The total resistance is equal to the external load, and this is known as stress.
There are several types of stresses. There is a shear stress, which can be defined as a stress which is applied parallel to a face of the material, and then the normal stress, which is applied perpendicularly to the face of the material. Strain happens when a material is subjected to distortive forces. When the forces are removed, and if the load is small, the distortion will generally disappear. However, if the load is significant, the material may not come back to its original shape. The degree of distortion can be defined as strain.
Then there is Poisson's ratio. Poisson's ratio can be defined as the ratio of the transverse strain perpendicular to the applied load to the axial strain in the direction of the applied load in a material under tensile load.
Using MATLAB, we plotted the expected axial stress, sigma y, as a function of the distance from the center of the hole. The graph shows that the stress is highest at the edge of the hole and decreases as we move away from the hole towards the rest of the plates.
This animation was created using the finite element analysis software built into SOLIDWORKS. It shows the normal stress in the plate along the load axis. You can see that in the beginning, the plate starts out with no stress. This is somewhat idealized, but works for our purposes. As the load, symbolized by the vectors, is applied, the plate stretches and stresses build in the plate. The highest tensile as well as compressive stresses occur along the edge of the hole.
Please note that while the colors of these images do not match those in the video, using the corresponding key the same information is conveyed. This plot shows the final normal stresses in the plate. And this plot shows the final shear stresses in the plate. To observe this effect in real life, we use the InStrong machine. Using a polarized light source behind the sample, the polarizing filter on our camera captured the polycarbonate being loaded and unloaded. This video is of the sample being loaded. We can see that the colored regions become closer together and multiply closer to the hole. This corresponds to the higher stress concentration at the edges of the hole. This clip shows the same sample but focuses on the fixed portion of the plate. One notices the increase in stress near the fixed clamp and can compare this to the uniform colors in the other regions of the plate.
Using the data obtained during the loading and unloading trials, we created this plot conveying the normal stress in the plate. The results match our prediction that the stress concentration would be highest at the edges of the hole. The shear stress also reflects what is depicted in the FEA models.